and also how to detail it from the data we get from ETABS. As we all know, a column is a vertical structural member which is defined to support axial compression load. It is an essential part of building structures such as bridges, high-rise buildings, and industrial plants. The specifications of column may vary depending on the specific requirements of structures, including load-bearing capacity, height, and other conditions. There are some specifications that are typically considered when designing columns include first one is column size. The size of the column is determined by the load it is expected to bear, as well as the height of the column. And the second thing is material. The material which is used for the column depends on the load capacity required and the environmental conditions. Common materials for columns include steel, concrete, etc. And then the cross-sectional shape. And third specification is its cross-sectional shape. The cross-sectional shape of the column can affect its load-bearing capacity and its stiffness. Common shapes include circular, rectangular, and square. And the next specification is its wall thickness. The wall thickness. Wall thickness of the column affect its strength and stability. It is typically designed to resist buckling, which is a failure mode that occurs when a slender column is subjected to compressive loads. And the next specification is its connections. The connections between a column and the other structural members such as beams and foundation must be designed to transfer the load safely and efficiently. These are the specifications which is essential in ensuring that a column is designed to meet its specific requirements of the structure. Yes. Now, other factor which is really important when we detail column is design column is its L by D ratio. L by D ratio is an essential factor to consider when designing a column because it affects its ability to resist buckling. Buckling is a type of failure mode which that occurs when a slender column is subjected to compressive load, causing it to deflect laterally. The buckling load of column decreases as its L by D ratio increases. For example, a column within an L by D ratio of 10 will have a lower buckling load than a column with L by D ratio of 5, assuming all other factors are equal. This is because the longer column is more susceptible to buckling due to its slenderness. In structural design, the L by D ratio of column is often used to determine its allowable axial compressive load capacity. And the maximum allowable axial load for column is typically calculated based on its cross-sectional area, material properties, and L by D ratio, as well as other factors such as loading, the type of support, and the material strength. These are the some points which you need to know when you detail column, and and now I will share the screen to show how you detail a column from the values you get from ETAB. My screen is visible?
Yes.
Okay.
Yes.
Yes. From ETAB, we will get the area of steel of column. For this, you have to go to the 3D mode, and then you have to analyze this structure by clicking on the concrete. This structure is a concrete structure, and you have to analyze the structure by clicking the concrete frame design. The software is analyzing the structure. After analyzing, it shows the area of steel required for each member. You can see this is the plan view of the same structure. You can see the beams AST, area of steel here. And here you can see the area of steel of columns here. Columns as well as beams here. Now we only looking into the column part. So we'll only select all the columns. For this, you have to go to select, and object type, and then columns. Select. Now all the columns have been selected, and then you right click on it and click on show selected objects only. Now you will see only the columns from the structure. Here, these are all columns. You can open the plan of the structure in this window. You can get it from here, like add new window. If you add new window, you will get another window, and here you can go to the plan and select the floor and apply. We got this like this. I just showed you. And then, yes, now you have to select the column. We have to define and detail each column. So we will start from here. I'll show you the detailing of only one column. It's same for all. So for this, you have to select the column which you want to detail in the plan window. And when you select it in the plan window, it will also appear in the 3D window. You can see here also. So you have to just rotate it so that you will see the AST clearly. Yes. This is the column. And here you can see the area of steel required. This is the area of steel, 1,500, 700 for this column, and 1,200 is for this column. Out of all these values, you have to select the maximum value. Yes, the maximum of steel is 2,530. This is the maximum AST in this column. So we have to design this column for this AST. So after the concrete frame design, you get the AST, and you have to select the maximum AST, and which is 2,530. And then you have to just check it by right clicking it. It will shows the AST of different combination, and it is a maximum 2,530. It is in the combination of 1.5 dead load plus dead load minus earthquake. If yes, we have the AST for one dead load live load condition. It is the major main combination. We can't ignore the AST of this combination. 1.5 dead load live load is the main combination. So 2,163 is the AST for the service condition. But we got 2,530 as the maximum, and we will look at it. Yes, how many combinations are there which is above 2,000 AST? We'll look into that. So we got 1, 2, for 1.5 dead load earthquake load, we got 2,426, and for this combination, we got 2,530. It is the AST. And yes, we got, yeah, above 2,000, we got this, and in the dead load live load also we got this. So we have to design it for AST greater than 2,000. That is sure. So we'll go to the AutoCAD, and yes, this is the column. This is the column. Ignore this. This is the pile. But we are only looking into the column part here. So this is the column and its AST is above 2500. It if the AST is 2530 only for this combination, then there is no need to design it for that particular AST, because it's only for this that combination. Then we can ignore it and go for the lesser value. But if it's for more than 2, then we can't ignore it. We have to design it for that AST. So we have to design it for AST of greater than 2000. So how to give the bars in that column? We got the AST. Now we have to calculate the number of main bar required for this column. Yes, C4. C4. First, we have to note that the cross section of the column, which is 300 by 500. So we draw a column of, this is the sectional, this is a plan view of a column. So this is the 300, we draw the 300 and 500 side column. And then we have to calculate how many number of main bars are required. For this, first we have to fix the diameter of the bar. Since it's a very big cross-sectional area, like it's a 300 by 500 column, so we can use a 20 mm diameter bar, and its AST is also very high. So we can, yes, it's C4. So yes, this is C4. Yes, it's a 300 by 500, and we are fixing a diameter. We can give diameter of 12 mm, 16 mm, 20 mm. We can give diameters of bar like this, 16, 20, and we can also give 12 mm bar as main bar. But here, since it's a very big column, we are and its AST is high, we are starting it with 20 mm bar. And then now AST is fixed and the diameter of the bar is fixed. Now we have to calculate how many number of bars are required. For this, we have to divide the maximum AST required divided by area of this 120 mm dia bar. What is the area of 20 mm dia bar? It's pi by 4 into 20 square. So let's calculate its AST of 1 bar. Is 0.785 into 20 square. It is 340 mm square. The diameter of 1 bar is 340 mm, and the maximum and the AST required for this column, as we saw here, is above 2000, above 2500. So we have to divide the 2500 divided by 340. So we got a value as 7.9. So we round it up to 8 numbers. So yes, that's why we got, that's why we gave this 8 number of 20 mm bar in the C4. Yes, here in this layout, we give names to the columns. And we give names and group all these columns based on their cross-sectional area and the area of steel. We group it like that. Like it is a C4 column. And where is other C4? There is, yes, there is only one C4. Yes, there is another C4 here. So the steel at the cross-section of these two columns are same. That's why its naming are same. C4. This is also C4. So the schedule of this column is this C4. In yes, so 300 and 500 mm column of and the main bar is 8 numbers of 20 mm dia main bar. So we got all the details of the column from this column schedule. Yes, how to give it? We give a tie like this, and inside this tie, we give 1, 2, 3, 4. 4 number of main bar, and then another tie is this. Inside this, we give the another 1, 2, 3, 4. Total 8 number bars, and this is the tie bars, and this is the main bars. And the tie bars is normally we give at 100 mm spacing. 8 mm we use 8 mm dia bar as tie bars, and the distance between these tie bars are what 100 mm. And the main bar, this is the tie bar, and the main bar is this, and it is 8 number of 20 mm dia. That is the detail of this column. Like this, we analyzed all the column. We selected each and every column, and we noted its cross-sectional area, and then noted the maximum AST coming under this column, and then find out the number of steel required for this particular column. And after getting all these columns details, we group the columns which we can group, like which columns are similar. We grouped it, and then this column schedule is made like this. Yes, if we are fixing the 16 mm dia bar as main bar, then how will we give? We have to calculate the area of steel of 116 mm bar, and then divide the maximum AST under that column. Divide it with that, then we will get the number of bar. Yes. I will show you how a section of a column look like. Like as I said, it is the plan view. If it is a section, then this is the tie bar at 100 mm spacing. Like it will provide like this, and it continues towards the end. And then in this column, there is main bar like this. This is the main bars. Yes, there it will be in the opposite side also. Opposite side also there will be main bar. This only we can see only one side in the cross-sectional view. Yes, it is the plan view which is shown here, and this is the tie bar which is this, and it is the main bar which is this. Hmm. Yes, this is how you detail the column from the values you get from ETAB. Yeah, that's it. This is all about detailing of column. If you have any doubt, you can ask. Does anyone have any doubt? Okay, then I will also share one thing. That is, yes. This is the column size of this is a 300 by 5. It is 300 by 500 column. If its size is less, then we'll see what happens. All story. Select this column, assign, frame, section property, column 200 by, yes, 200 by 400. Let's put this. And then just analyze it. Yes, here as you can see, the column is filled because the load is coming under this column is more than this column can carry because its cross-sectional area is less. That's why it's failed. So yes, as you can see here, the AST is not showing. It shows it's overstressed. It means it's failed. So we have to increase its cross-sectional area to make it safe. And here you can see how it is failed. Like if you right click it, you can see the details. And here by clicking the details, you can get the all details. Yes, here it is shows why it failed. It is failed due to its reinforcing required exceeds the maximum allowed. Because the AST which we have to give in this column is more than this column can accommodate because its column size is less. If in 200 by 400 column you can't give 10 number of 20 mm diameter bar because it's very small column, so it will be very congested and this column is very small to accommodate this steel. So we have to increase this cross-sectional area of column to accommodate all the bars which required for that particular column. So for that, we have to increase its cross-sectional area. Look at this. Its cross-sectional, its AST is 4,390, which is very high for a 200 by 400 mm column. In normally, we say that 2% of AST should be area 2% of area of cross section should be given as its maximum AST in normal case. For if inside we are pouring concrete inside this column, so its bars are congested. We can't pour the concrete easily. All the element of in the concrete will not reach in all the place of this column. So we can't congest. We can't give all these bars in this short column. So we have to increase its area. Its AST is 4,390 and we normally give 2% of area of cross-sectional area. So 2% of cross-sectional area is 2 divided by 100 into 200 by 400 column. The maximum AST which we give in a 200 by 400 column is 1,600 mm square. It's not actually maximum, but it's better to give a maximum of 1,600 mm square area steel in a 200 by 400 column. So maximum. So we are giving is 1600, but in that, if we look at it, we get 4390, which is very high. So we can't give it into this column. So that's why we increase its column size. Select it, assign frame section property, and give the next column size, which is it is fail in 200 and 500 also. So that's why I gave it as 300 by 500. Column 300. Yes, now this column is safe. It's ASD 1500, 4500, 4056. It is okay for a 300 by 500 column, but not for 200 by 400 column. So yes, as you can see, all the elements are safe in this because we gave the sufficient column size. So you have to design it like this. No column should be failed. And if column is failed, then you can right click on this and go to the detail and figure out why it failed from here, from this details. It's safe. That's why it's not showing anything in this here as remark. But previously we saw that there was a remark and it shows that the cross sectional area is less. That's it. If there is any questions, then you can ask. Otherwise, we can wind it up.
Anyone has any questions? Thank you, Srishma.
Thank you.